March 15, 1945. Somewhere along the shattered Rhine Valley in western Germany, Captain Sarah Mitchell stood knee-deep in mud beside what had once been a critical railway junction, watching as German reconnaissance teams observed from distant hillsides through binoculars, documenting what they assumed would be weeks of American delay. The railway bridge lay twisted in the river below, its steel girders bent like paper clips, the approaches cratered by demolition charges the retreating Wehrmacht had detonated just 18 hours earlier. Around Mitchell, German civilians who had survived the bombardment whispered among themselves that the Americans would need at least a month to restore rail service, that their vaunted engineering corps would bog down in the same logistical nightmares that had plagued German reconstruction efforts throughout the war. What none of them understood, neither the watching German soldiers nor the skeptical civilians, was that in those mud-filled craters and twisted rails lay not an obstacle, but an opportunity, and that the engineering doctrine which would rebuild this junction before sunset was already being implemented by crews who had practiced this exact scenario dozens of times in training facilities back in Virginia. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The mathematics of American logistical dominance were being written not in the spectacular tank battles that would capture headlines, or the strategic bombing campaigns that flattened German cities, but in the quiet technical revolutions of railway engineering, prefabricated construction, and industrial standardization that allowed American forces to rebuild infrastructure faster than German forces could destroy it. This pattern of mutual misunderstanding and technological contempt had begun long before the first American engineers landed in Normandy. The arrogance started in the winter of 1943, when German intelligence officers analyzing American railway equipment captured during the North African campaign filed reports that seemed to confirm every prejudice about American engineering philosophy. The equipment was crude by German standards, built with loose tolerances, constructed from standardized components that could be assembled by semi-skilled workers, rather than requiring the precision craftsmanship that characterized German railway engineering. Colonel Heinrich Weber, a railway specialist assigned to German military intelligence, had examined captured American railway cars, locomotives, and construction equipment with professional disdain. The American approach offended his engineer's sensibility. Where German railway equipment featured precision machined components built to exacting specifications, American equipment used rough castings and stamped parts held together with bolts rather than welds. Where German locomotives represented the pinnacle of steam engineering with carefully calculated thermodynamic efficiency, American locomotives were brute force machines that sacrifice elegance for raw power and ease of maintenance. Where German railway construction required skilled crews working with surveying equipment and engineering tables to ensure proper grades and alignments, American methods used pre-calculated standard designs that could be implemented by crews with minimal technical training.
Weber filed a comprehensive report concluding that American railway engineering was fundamentally inferior to German methods, that the crude equipment and simplified construction techniques reflected a nation that valued quantity over quality, mass production over craftsmanship. The report noted that American railways, while adequate for the vast distances and gentle terrain of North America, would prove inadequate for the demands of European warfare, where precision, durability, and efficiency were paramount. This assessment, based on genuine observation but reflecting profound misunderstanding of American engineering philosophy, would prove catastrophically wrong. What Weber and his colleagues failed to understand was that the apparent crudeness of American equipment was not a sign of inferior engineering, but rather a deliberate design philosophy optimized for rapid deployment, field repair, and logistical flexibility. The contempt flowed both directions in the years before American forces engaged German armies directly in Europe. German military planners, confident in the superiority of their engineering and organizational capabilities, dismissed American industrial capacity as quantity without quality, mass production of inferior equipment that would crumble under the demands of modern warfare. This attitude permeated German military thinking at the highest levels. Field Marshal Gerd von Rundstedt, commanding German forces in the West, had stated in planning conferences that American engineering units would prove incapable of maintaining supply lines across the difficult terrain of France and Germany, that the vaunted American industrial capacity would be strangled by logistical incompetence. These assumptions rested partly on German experiences fighting Soviet forces, where crude equipment and simplified tactics had initially proven vulnerable to German technical superiority, and partly on racist contempt for American culture that German propaganda portrayed as soft, materialistic, and lacking the martial discipline necessary for sustained combat operations. German intelligence assessments confidently predicted that American supply lines would collapse under pressure, that American engineering units would require weeks to repair damaged infrastructure, that the careful demolition of railways, bridges, and roads during German retreats would bog down American advances and buy time for German counterattacks. These predictions would cost Germany the war, as American engineering capabilities exceeded German projections by orders of magnitude. The cost of this intelligence failure became apparent almost immediately after American forces broke out of Normandy in August 1944. German forces retreating across France implemented a scorched earth policy targeting transportation infrastructure, systematically destroying railway bridges, cratering rail beds, demolishing switching yards, and sabotaging locomotives and rolling stock they couldn't evacuate. The demolitions were thorough and professional, executed by combat engineers who understood railway construction and knew exactly where to place charges for maximum destruction. Each demolished bridge, each cratered junction, each destroyed marshalling yard represented what German planners calculated as days or weeks of delay for American supply lines. Then American railway construction battalions arrived at the destruction sites, and the carefully calculated delays evaporated like morning fog under summer sun. On August 30, 1944, elements of the 713th Railway Operating Battalion reached the demolished railway bridge over the Seine at Conflans, a critical crossing point for supply lines supporting the advance toward Germany. German engineers had blown the bridge on August 25, dropping all 5 spans into the river and cratering the approaches with demolition charges that left holes 15 feet deep.
German intelligence officers calculated this would require American engineers at least 3 weeks to repair, providing time for German forces to establish defensive positions along the German border. Captain Sarah Mitchell, commanding the lead company of the 713th, stood on the western bank surveying the destruction through binoculars, while her executive officer, Lieutenant Rebecca Chen, coordinated with the bridging units already moving forward with prefabricated components. Mitchell was 32 years old, a civil engineer from Pennsylvania who had worked on railway construction before the war and had volunteered for military service after Pearl Harbor. She had spent 18 months in training commands, learning not just how to build railways, but how to rebuild them under fire, how to assess damaged infrastructure and implement repairs with maximum speed, how to coordinate equipment and personnel for continuous operations. She looked at the demolished bridge and saw not an obstacle, but a textbook problem she had solved dozens of times in training. Preparing and narrating this story took us a lot of time, so if you're enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Mitchell's company began work at 0600 hours on August 31st. While one platoon cleared the approach craters and laid temporary track, another assembled prefabricated bridge sections on the western bank. The bridge design was pure American engineering philosophy, built from standardized steel components that could be bolted together by crews working from illustrated manuals rather than detailed engineering drawings. Each component was numbered and color-coded,
Assembly required following sequential instructions rather than understanding structural engineering principles. The design sacrificed elegance and efficiency for speed and simplicity, accepting higher material costs and reduced load capacity in exchange for construction speed that German engineers considered impossible. By 1400 hours on August 31st, 14 hours after beginning work, the first bridge span was in place. By 2200 hours, all 5 spans had been erected and approach tracks laid. At 0630 hours on September 1st, 36 hours after beginning work, the first American locomotive crossed the new bridge, pulling freight cars loaded with ammunition and fuel for units advancing toward the German border. German observers monitoring the crossing from distant positions reported the bridge completion to headquarters, where intelligence officers initially dismissed the reports as errors or exaggerations. When aerial reconnaissance confirmed that the bridge was indeed operational, German planners were forced to recalculate their assumptions about American engineering capabilities. The pattern repeated itself across France and into Germany throughout the autumn and winter of 1944. German forces demolished infrastructure with professional thoroughness. American engineers rebuilt it with assembly line efficiency that German planners found incomprehensible.
Infrastructure was built from prefabricated components, manufactured in factories far from the construction site, shipped forward in standardized packages, and assembled by semi-skilled crews following illustrated procedures. The approach sacrificed long-term durability and engineering elegance for construction speed and logistical flexibility. Bridges built with this method would need replacement after the war, but they could be erected in days rather than weeks. Track laid with simplified methods would require more maintenance, but it could be operational in hours rather than days. More fundamentally, American engineering doctrine accepted waste and redundancy as acceptable costs for speed. Where German engineers carefully calculated minimum requirements and built precisely to specification, American engineers overbuilt everything, using more material than theoretically necessary, accepting higher transportation costs for the certainty that components would fit and function even under imperfect field conditions. This philosophy infuriated German engineers who examined captured American equipment and saw inefficiency and waste, but it meant that American construction proceeded without the delays that plagued German efforts when precision components didn't fit properly or when unexpected conditions required design modifications. The railway junction at Conflans was merely the first of dozens of similar projects. At Chalons, American engineers rebuilt a demolished switching yard in 5 days that German estimates said would require 3 weeks. At Reims, a completely destroyed locomotive repair facility was rebuilt and operational in 9 days, using prefabricated building sections and standardized repair equipment. At Verdun, a railway tunnel collapsed by German demolitions was cleared and reinforced in 12 days, using techniques that prioritized speed over permanence, but delivered operational capacity when it was needed. Each project followed the same pattern. German forces demolished infrastructure thoroughly and professionally. German intelligence calculated delays based on German engineering capabilities and methods. American engineers arrived with prefabricated components, standardized procedures, and assembly line techniques that reduced reconstruction time to fractions of German estimates. German commanders, their retreat strategies based on assumptions about American engineering limitations, found themselves outpaced by supply lines that stretched forward faster than German forces could retreat and regroup. The most spectacular demonstration of American railway engineering capabilities came in March 1945 at the Rhine crossing operations. German forces making their final stand along the Rhine River demolished every railway bridge across the river with meticulous care, understanding that preventing American supplies from crossing the Rhine would be critical to any hope of sustained defense. The bridge at Remagen, famously captured intact by American infantry before German engineers could complete its demolition, provided one railway crossing, but it was insufficient for the massive supply requirements of American forces pouring across the Rhine for the final offensive into Germany. On March 15, 1945, Captain Sarah Mitchell received orders to construct a new railway bridge across the Rhine at a location where German forces had demolished the original structure so thoroughly that even the foundation piers had been destroyed. The site was under intermittent German artillery fire. The approaches were mined.
The river was running high with spring snowmelt, flowing fast and cold and dangerous. German intelligence officers calculated that constructing a railway bridge at this location would require American forces at least 6 weeks, by which time German defenders would have established fortified positions in depth, making further American advances prohibitively costly. Mitchell stood on the western bank on the evening of March 15th, watching the fast-moving water and the cratered approaches, calculating requirements and coordinating with bridging units, engineering battalions, and railway construction companies. Her forces included over 800 personnel, dozens of cranes and earth-moving machines, hundreds of tons of prefabricated bridge components, and supply lines stretching back through Luxembourg and France to ports on the English Channel. She had equipment, personnel, and materials. What she needed was time, and time was precisely what German artillery in the approaching spring offensive schedule would not provide. Mitchell organized her forces for continuous 24-hour operations, with crews rotating through 8-hour shifts so that work never stopped. Floodlights illuminated the construction site at night, making it visible to German artillery observers, but necessary for maintaining work pace. Construction began at dawn on March 16th, with pile-driving operations to establish foundation piers in the river bottom. Dangerous work conducted from pontoon platforms, while engineers in diving suits worked underwater guiding pile placements despite the cold and current. German artillery began ranging fire on the construction site within hours, shells exploding in the river and on the approaches, killing 3 engineers and wounding 17 in the first day. Mitchell, moving constantly between work sites coordinating operations, refused to halt construction. Medical units established aid stations at both ends of the bridge site. Casualties were evacuated immediately and replaced by fresh personnel from reserve companies held back for exactly this purpose. The work continued without pause despite the artillery fire that made every moment at the bridge site potentially lethal. By March 18th, foundation piers were complete and bridge girders were being lifted into place by heavy cranes working from both banks. The assembly process looked like chaos to German observers watching from distant hillsides, dozens of separate activities proceeding simultaneously without apparent coordination. Cranes lifting components, while welding crews secured connections, while track-laying crews prepared approaches, while supply trucks delivered materials in endless streams. But the apparent chaos was carefully orchestrated. Every activity timed and positioned to support every other activity. The entire operation proceeding according to detailed plans that had been rehearsed repeatedly in training exercises. German artillery intensified as the bridge took shape, ranging fire with increasing accuracy, scoring direct hits on crane platforms and bridge components. On March 19th, a German shell struck a crane lifting a bridge section, killing the crane operator and sending the section tumbling into the Rhine. Mitchell, coordinating from a command post on the western bank, immediately ordered a replacement section moved forward and assigned a new crane crew. The destroyed section was written off without attempts at recovery. The replacement was in position and being lifted within 3 hours. German engineers, observing this response, realized that American logistics included sufficient redundancy to absorb losses and continue operations without delay, a level of material abundance that German forces operating with scarce resources could not match.
By March 21st, bridge spans were complete, and track-laying crews were working on both approaches, grading roadbeds, placing ties, spiking rails, and installing switching equipment. German aircraft, scarce by this point in the war but still capable of isolated attacks, attempted bombing runs against the bridge on March 22nd. American anti-aircraft batteries surrounding the construction site shot down 2 aircraft and drove off the others. One bomb hit near the eastern approach, cratering the roadbed and destroying 50 yards of newly laid track. Repair crews filled the crater and relayed the track in 6 hours, working under floodlights while German artillery continued intermittent harassment fire. At 0730 hours on March 23rd, 7 days after beginning construction, the bridge was complete. Mitchell, exhausted from days of continuous operations, stood on the western approach as the first American locomotive, a massive freight engine pulling flat cars loaded with tanks and artillery pieces, approached the new bridge at walking speed, the engineer watching nervously as his locomotive moved onto the fresh structure. The bridge held. The locomotive continued across, followed by car after car of military equipment,
rolling steadily across the Rhine and continuing eastward toward the advancing American forces that were breaking through German defenses and driving toward the heart of Germany. German commanders receiving reports that the Rhine Bridge was operational just 7 days after construction began initially refused to believe them, insisting that intelligence reports must be in error or that the bridge was a temporary structure incapable of supporting heavy loads. When aerial reconnaissance confirmed that American tanks were crossing the bridge and that heavy freight traffic was proceeding continuously, German military planners were forced to abandon defensive strategies predicated on American supply difficulties. The American engineering achievement represented not just successful construction, but the collapse of German strategic assumptions about their enemy's capabilities. The transformation in German military thinking about American engineering capabilities after the Rhine crossing represented one of the most dramatic intelligence reversals in modern warfare history. Throughout the winter of 1944 and early spring of 1945, German commanders had based defensive strategies on assumptions about American logistical limitations that proved spectacularly wrong. The speed with which American engineers rebuilt infrastructure, the abundance of equipment and materials they deployed, and the organizational efficiency with which they coordinated massive construction projects under fire exceeded German projections by factors that made previous intelligence assessments look laughable. Field Marshal Albert Kesselring, commanding German forces in the West after von Rundstedt's dismissal, filed reports to Berlin stating bluntly that continued resistance was militarily futile because German forces could not destroy infrastructure faster than American engineers could rebuild it, that the material abundance and engineering capabilities of American forces made defensive strategies based on demolition and delay ineffective. What German intelligence had failed to understand was that American engineering superiority rested not primarily on individual skill or technical innovation, but on industrial organization, logistical systems, and engineering doctrine that treated construction as a manufacturing process rather than a craftsmanship endeavor. Captain Sarah Mitchell, standing beside the completed Rhine Bridge, watching supplies flow eastward in an endless stream, understood this instinctively because she had been trained in this philosophy and had seen it work repeatedly.
American engineers were not necessarily more skilled than their German counterparts, and American equipment was not necessarily more sophisticated, but American doctrine emphasized speed, standardization, and acceptance of waste in ways that German engineering culture found incomprehensible and that German military planning had failed to account for adequately. The Rhine Bridge project illustrated every advantage of the American approach and every limitation of German countermeasures. Mitchell's forces had suffered 43 casualties during the construction, including 12 killed, but the casualties had not slowed operations because replacement personnel were immediately available from reserve units. German artillery had destroyed equipment and materials worth hundreds of thousands of dollars, but the destroyed items had been replaced from supply stocks without affecting construction timelines because American logistics included redundancy that assumed losses and prepared for them. German air attacks had caused damage that would have been catastrophic to forces operating with minimal resources, but American repair capabilities and material abundance meant that damage was repaired faster than German forces could inflict it. More fundamentally, the entire project reflected engineering doctrine that German military culture struggled to comprehend. The bridge was not built to last. It was built to function immediately. The materials were not used efficiently by German standards. They were used abundantly to ensure success despite imperfect field conditions. The construction methods were not elegant, they were fast. Every design decision prioritized immediate operational capability over long-term durability, current needs over future efficiency, speed over economy. This philosophy infuriated German engineers who examined the completed structure and saw waste and inefficiency, but it delivered a functional railway bridge across the Rhine in 7 days, and 7 days was what the advancing American armies needed. The pattern Mitchell had demonstrated at the Rhine repeated itself across Germany throughout the final months of the war as American forces drove deeper into German territory and German forces retreated, demolishing infrastructure in increasingly desperate attempts to slow the advance.
At Kassel, American engineers rebuilt a completely demolished railway yard in 11 days using prefabricated components and standardized layouts. At Erfurt, a tunnel complex collapsed by German demolitions was cleared and reopened in 8 days using earth-moving equipment on a scale German forces could not match. At Leipzig, an entire railway network damaged by Allied bombing and German demolitions was restored to operation in 16 days through coordinated efforts by multiple engineering battalions working simultaneously on different sections. Each project followed similar patterns and demonstrated similar advantages. American forces arrived with abundant equipment, prefabricated materials, and detailed plans for standard construction approaches. German demolitions, however thorough, could not destroy infrastructure faster than American engineers could rebuild it using industrial methods that treated railway construction as assembly line production. The logistical systems supporting American engineering operations ensured continuous material flow despite the enormous distances from ports to forward construction sites. The organizational efficiency of American engineering units meant that personnel, equipment, and materials converged at construction sites in coordinated sequences that maximized productivity.
Lieutenant Rebecca Chen, Mitchell's executive officer, had developed a saying that captured the essential truth about American engineering superiority during those final months in Germany. Standing beside yet another demolished railway junction watching crews begin reconstruction work, Chen would tell newly arrived replacement officers that the secret to American success was simple but profound. German forces, she explained, built railways the way craftsmen built furniture, carefully and individually. American forces built railways the way factories built automobiles, systematically and repeatedly. German methods produced better railways if you had unlimited time and resources. American methods produced adequate railways immediately, and immediately was what mattered in warfare. The most dramatic illustration of this philosophy came in April 1945 during operations supporting the encirclement of the Ruhr industrial region, where 300,000 German troops were trapped by American forces, cutting their supply lines and methodically reducing their defensive perimeter. The operation required American forces to maintain supply lines across terrain that German forces had devastated during their retreat, demolishing every railway, bridge, and road crossing they abandoned. German commanders trapped in the Ruhr pocket had calculated that American supply difficulties would prevent sustained offensive operations, buying time for relief forces that German high command no longer possessed the strength to assemble. Mitchell, now promoted to major and commanding an entire railway construction battalion, received orders to establish rail connections supporting forces closing the Ruhr encirclement from the south. The mission required rebuilding over 60 miles of railway line that German forces had systematically destroyed, including 14 demolished bridges, 3 collapsed tunnels, and dozens of cratered sections where German engineers had blown up the rail bed itself. German intelligence officers calculated this would require American forces at least 8 weeks. Mitchell's orders specified completion in 3 weeks. She organized her battalion into 3 separate construction groups, each assigned a specific section of the route and each equipped with complete sets of personnel, equipment, and materials necessary to work independently. The groups would work simultaneously on different sections rather than sequentially on one section at a time, accepting higher coordination complexity for faster overall completion. Each group received standardized bridge designs, tunnel clearing procedures, and track laying specifications that eliminated the need for custom engineering at each site. The approach was pure industrial organization applied to military construction, treating the entire 60-mile railway reconstruction as 3 parallel assembly processes rather than a single sequential construction project. Construction began on April 7, 1945, with all 3 groups commencing work simultaneously at their assigned sections. Group Alpha, commanded by Captain Jennifer Walsh, focused on the northern section including 5 demolished bridges and 1 collapsed tunnel. Group Bravo, commanded by Captain Maria Rodriguez, took the central section with 6 bridges and 2 tunnels. Group Charlie, commanded by Captain Elizabeth Thompson, received the southern section with 3 bridges and the longest stretch of cratered railbed. Mitchell established a coordination headquarters at a central location and spent her days traveling between groups by jeep and liaison aircraft, monitoring progress, resolving supply issues, and adjusting priorities as circumstances changed.
The scale of operations exceeded anything American engineering forces had attempted previously in the European theater. Over 2,000 personnel worked simultaneously across 60 miles of devastated terrain. Hundreds of trucks delivered materials in continuous convoys from supply depots established at captured German railway yards. Dozens of cranes, bulldozers, pile drivers, and specialized equipment operated at multiple sites. The supply requirements alone were staggering. Thousands of tons of steel for bridges, hundreds of tons of explosives for clearing demolitions, endless supplies of rail, ties, spikes, ballast, and all the countless components necessary for railway construction. German forces, still holding positions in the rural pocket and along the flanks of the construction route, attempted to disrupt operations with artillery fire and occasional infantry raids. American security forces, combat engineer battalions assigned to protect construction crews, established defensive perimeters around each worksite and conducted aggressive patrols to push German forces back from artillery range. Air support, increasingly abundant as Allied air superiority became total, struck German artillery positions and supply routes supporting German forces near the construction corridor. The construction proceeded despite harassment that would have halted German engineering operations, but merely slowed American work without stopping it. By April 15th, 8 days into the project, Group Alpha had completed 3 bridges and cleared the tunnel, laying track continuously behind the advancing construction front. Group Bravo had erected 4 bridges and was working on tunnel clearing operations complicated by unstable geology that required more extensive shoring than standard procedures specified. Group Charlie had filled the cratered sections and was laying track while simultaneously beginning bridge construction at their assigned crossings. Mitchell, monitoring progress from her coordination headquarters, calculated they were ahead of schedule despite losing equipment and personnel to German harassment fire. The project revealed advantages of American engineering doctrine that extended beyond mere construction speed. When Group Bravo encountered unexpected difficulties with tunnel clearing, Mitchell redirected equipment from Group Charlie without disrupting either group's overall operations because the standardized equipment meant that bulldozers and support gear from one group could be immediately employed by another group without requiring specialized training or adaptation. When German artillery destroyed a crane at one of Group Alpha's bridge sites, replacement equipment arrived from supply depots within 18 hours because American logistics maintained reserves of critical equipment specifically for replacing losses. When construction at one site exceeded material estimates, supplies were diverted from other sites without causing shortages because American logistics officers routinely overordered materials, assuming that actual consumption would exceed engineering calculations. The flexibility this abundance provided was something German forces, operating with scarce resources and rigid logistics, could not match. German engineering required careful planning and precise execution because materials were limited and mistakes were costly. American engineering accepted mistakes and overcame them through material abundance and logistical flexibility. If American crews made errors in bridge construction, they tore down defective work and rebuilt it with fresh materials. If tunnel clearing required more explosives than initially calculated, additional supplies arrived without question.
If track laying encountered unexpected terrain difficulties requiring detours, survey crews mapped alternate routes and construction continued without waiting for approval from higher headquarters. On April 20th, 13 days after beginning work, Group Alpha completed their section and began moving south to assist Group Bravo with their remaining tunnel work. By April 23rd, all 3 groups had completed their major construction projects and were working on final track connections, installing switching equipment, and preparing the line for operational traffic. Mitchell, conducting final inspections by traveling the entire 60-mile route by railway inspection car, examined every bridge, tunnel, and track section, checking for defects that could cause delays once operational traffic began. At 0600 hours on April 25th, 18 days after beginning construction and 3 days ahead of the specified completion deadline, the first American locomotive traveled the entire 60-mile route, carrying supplies for forces completing the reduction of the Ruhr pocket. Mitchell, riding in the locomotive cab for the inaugural run, watched German prisoners of war working beside the track under guard, clearing debris and filling ditches, observed by German civilians standing silent and defeated along the route.
The railway her battalion had built in 18 days would have required German engineering forces 3 months to construct using their methods and resources, and everyone along the route understood what that disparity meant about the war's outcome. German commanders in the Ruhr pocket, receiving reports that American supply lines were now operating at full capacity despite their demolition efforts, understood that further resistance was futile. The pocket surrendered on April 18th, but the railway Mitchell's battalion had built continued operating, carrying supplies eastward for American forces driving toward Berlin and southward toward Bavaria. The railway would remain operational through the end of the war and into the occupation period, carrying not just military supplies but eventually humanitarian aid for German civilians facing starvation in the war's aftermath. The broader strategic impact of American engineering superiority during the final months of the European War extended far beyond individual construction projects. German defensive strategies throughout 1945 had been predicated on assumptions about American logistical limitations that American engineering capabilities systematically invalidated. Every German retreat relied on demolitions buying time for defensive preparations. Every German counterattack assumed American supply difficulties would create vulnerabilities. Every German defensive position anticipated that destroying local infrastructure would complicate American operations. These assumptions proved wrong consistently because American engineers rebuilt infrastructure faster than the enemy could destroy it. The psychological impact on German forces was severe and contributed to the collapse of military resistance in the war's final weeks. Soldiers fighting defensive battles saw their commanders ordering demolitions of bridges and railways that their own forces needed for supply and reinforcement, sacrificing German logistics to delay American advances. Then they watched American engineers rebuild the demolished infrastructure in days, restoring American supply lines while German forces remained cut off and undersupplied. The contrast between American abundance and German scarcity became impossible to ignore and impossible to overcome through courage or tactical skill. Mitchell, reflecting on the campaign years later, would describe the railway construction operations as the application of American industrial philosophy to military engineering, and would argue that this application was as important to Allied victory as tank production or air superiority. The ability to rebuild infrastructure faster than the enemy could destroy it, she explained, meant that defensive strategies based on demolition and delay became ineffective. The willingness to accept material waste and construction inefficiency in exchange for speed meant that construction could proceed under fire without crippling delays.
The organizational systems that treated engineering as industrial production meant that large-scale projects could be completed in time frames that traditional engineering approaches could not match. The final irony of the story involved German engineering personnel who had dismissed American methods as crude and inefficient, finding themselves after the war working for American occupation authorities rebuilding German infrastructure using American methods and equipment. Colonel Heinrich Weber, the railway specialist who had filed the 1943 intelligence report dismissing American engineering capabilities, spent the years 1946 through 1949 as a technical advisor to American railway reconstruction teams in the American occupation zone. He worked alongside American engineers, learning their methods and grudgingly acknowledging their effectiveness. In a 1948 interview with American military historians, Weber admitted that his pre-war assessment had been catastrophically wrong, that he had mistaken different engineering philosophy for inferior engineering capability, and that the apparent crudeness of American methods masked sophisticated understanding of how to optimize construction for speed rather than elegance. The lessons American engineers learned in Europe would influence American infrastructure development for decades after the war. The prefabrication techniques, standardized designs, and industrial construction methods developed for military engineering transferred directly to civilian construction projects. The interstate highway system, built during the 1950s and 1960s, employed engineering approaches and construction methods that had been refined rebuilding railways across France and Germany.
The rapid suburban development that characterized post-war America used standardized housing designs and assembly line construction techniques that reflected the same philosophy of speed and standardization over craftsmanship and individual design. Mitchell herself returned to civilian life in 1946, working initially for a major construction company before establishing her own engineering firm specializing in rapid infrastructure development. Her company worked on projects across the United States and eventually internationally, building railways, highways, bridges, and facilities using methods she had perfected during the war. She insisted that her civilian projects maintain the same emphasis on speed and standardization that had characterized her military work, arguing that construction delays cost money and created problems that careful planning and efficient execution could prevent. By the 1970s, Mitchell's firm had become one of the largest construction companies in the United States, known for completing complex projects ahead of schedule and under budget. Mitchell, interviewed for business magazines about her success, consistently credited her wartime experience, explaining that military engineering had taught her that speed was often more valuable than perfection, that standardization enabled efficiency, and that accepting higher material costs to reduce construction time was usually good business. She remained active in her company until her retirement in 1985, mentoring younger engineers and insisting they understand that engineering was ultimately about solving problems efficiently rather than demonstrating technical sophistication.
The story of American engineering superiority in World War II stands as a case study in how industrial organization and engineering philosophy can overcome initial technical disadvantages to produce decisive strategic advantages. German forces possessed excellent engineers, sophisticated technical knowledge, and proud traditions of precision and craftsmanship. American forces possessed industrial abundance, organizational flexibility, and engineering doctrine that prioritized speed and standardization. The contest between these approaches was decided not on drawing boards or in laboratories, but in muddy construction sites across Europe, where American engineers rebuilt infrastructure faster than German forces could destroy it, demonstrating that in warfare, adequate solutions implemented immediately defeat perfect solutions implemented eventually. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.